So now we will begin technical presentations. The first speaker will be Professor Chua. Before Leon comes up, let me briefly introduce Professor Chua. Probably doesn't need much introduction, but let me tell you that Leon was my teacher when I was a graduate student at Berkeley. In fact, part of my PhD thesis was on Memristor, extension of Memristor. He has received numerous awards for his great contribution, great leader in really many pioneering fields, including chaos and nonlinear science. And I think most recent development of Memristor has excited him to continue on. So you will hear a great theory from Leon Chua. So, Professor Chua.
Thank you very much. Good morning. Just want to remind you that this week is the 50th anniversary of the famous paper that launched nanotechnology. And in this very famous talk, I just want to remind you the famous statement Feynman had challenged that why cannot we write the entire 24 volumes of Encyclopedia Britannica on the head of a pin? And of course, we all knew that this has been made easily, and in fact, it is now possible to pack much more than that. We can have the whole Library of Congress on a Memristor chip as well. And but this is still conventional. Conventional electronic memories are, I could say, casting stones, in the sense that they have no minds. What I want to show you today, I hope, is that Memristors can learn. So my goal in this talk is to demonstrate that even simple Memristor-based, what I call toy circuits, can be actually endowed with a mind that can learn without supervision. And this is the reason why the title is called Memristor Minds. That's the title of my talk today. For those of you who, I assume most of you already know what Memristor is, but if you did not, I have a high school definition for that. So I call the layman's definition, and it's just 3 words. Memristor is pinch Ohm's law. That's all there is to it. Ohm's law normally in the voltage current plane is a straight line. Memristor is simply the resistance depends on the state, and that's that's the simplest definition. It's a pinch Ohm's law. Very accurate definition. Okay. Now, interestingly enough, my paper was published in 1971. Without knowing it, 2 years later, 1973, there was a biological Memristor that was revealed, although of course the scientists didn't know a thing about Memristor. But I just want to call your attention that, in fact, that this is a Memristor as well, 1973, and this has launched a major area of research that's very hot today. It's called LTP, and I'm going to come back to that a little later. And it has everything to do with our brain. So let's start with our brain. This is part of the section of that with all those wirings. But what's important, I want to call your attention, is that since our brains are made of two important things. The axons, which is the output, and all those contact that you make with the neighbors are called synapses. Forget all the other things are just, I just call them junk right now because they're not important, okay? And what you and I think are just made of these two things. And I want to convince you today that synapses, one of the two components of our brain, are in fact Memristors. And I will also want to show you that axons, the other major component, are also made of Memristors. So in other words, you might be surprised to learn today that brains are made of Memristors as far as intelligence is concerned. Okay, now let's go back to where are synapses Memristor. Well, synapses, essentially, as you remember, are just two. This is part of the end of the axon, and this is the dendrite, and then they don't actually make contact. There is a few angstrom gap of molecules that are called neurotransmitters that sneak through, and the amount of those molecules through is actually called the synaptic strength. This actually is exactly related to a memristor. If you look at memristor curve, the slope of the curve, it's called a resistance or memristance, is exactly the synaptic strength. And when you learn, you are trying to figure out how much of this neurotransmitter you want to emit. It's the same thing as going around this curve and find out what slope you want to be. And so that's really why synapses are memristors, okay? And in fact, memory, we now know that memory is coded in the synaptic strength, okay? And the neural substrate of memory requires long-lasting changes in synaptic strength triggered by past experience and activity. And this is part of the major discovery of the 1973 biological memristor I just told you about, and we're going to come back to that a little later, okay? And now, learning via synaptic wiring, okay? It turns out that synaptic connections in the living mouse brain rapidly responds to motor skill learning, and rewriting is actually permanent. And this is based on the paper just published two weeks last December, a very current paper. In other words, prior to this, most of these are sort of reasonable conjectures, hypotheses, but I will show you the real experiment that was being conducted. This is a mouse that that's asked to learn exercise. This is sort of a rod that's spinning. So it's like a treadmill. And this rod will keep going faster and faster, so the mouse has to learn to be faster and faster to stay in place. And then there is this instrument that's called a two-photon machine that would actually monitor how the synapse would behave. And I want to show you an interesting thing. So before the exercise, before the training, this is a real picture in vivo of these are the synapses. Now, after 2 days, you can see that these synapses are changed. This is getting smaller and this is getting bigger. So this is just one of many confirmations that indeed that this is how we learn, is that we just grow or remove part of this the growth, the synapses. Okay. Now, more recently, in fact, just last year, there is a very interesting paper that shows that if you this is a paper that I want to show you that they actually use a memristor to reproduce a behavior. Oh.
Piece of little.
Is that better? Thank you very much.
Little mechanical engineering.
Fantastic. Thank you. Thank you very much. So now this is very interesting because so when you learn, you typically have two neurons that communicate with each other, and this is the synapse that is magnified here. And now, in a very famous experiment by Professor Pu, actually from Berkeley neurobiology department, it is now a classic paper. He actually, I'm just quoting his statement. He said, activity-dependent changes in synaptic efficacy or connectivity are critical for the development of signal processing and learning of the nervous system. And if you would just change the wording, instead of memristor, this I will just cross this out and call this memristance. And then this would be the same, except that we now call this intelligent system, electronic systems. This would actually apply word for word. And as I said, this is the famous paper now that is a standard reference. And what Professor Pu did was to actually make this ingenious measurement on the real neuron, living neuron, and show that when you learn, there is a 20 millisecond window. And it all depends on whether, remember, you have the presynaptic and postsynaptic, and you have all this action potential going on. It all depends on whether you are ahead or behind. If you are ahead, and as long as you're within the 20 millisecond window, you will learn. And the best is when you are exactly coincident, then you have maximum learning, meaning that you would grow more protein in some sense. And as you get a little bit away, you grow less. Whereas if you are behind, which means that it's not important, it actually would have been a negative. It actually inhibits the thing. So this is basically, I call this a dual exponential curve, which is the standard curve now that everybody is basing on. And so now this is neuron nearing and learning. Suffice to say that this is how you and I learn, at least as we know it today. And now this paper that I'm referring to is from Linares Baranes and his colleague. And he says that membristors can explain spike time dependent plasticity. This is the code is STDP that you saw in neural synapses. And what they did is quite interesting. They just took these synapses and they put in memristor instead of these neurotransmitters, and they demonstrated that if you pick a memristor curve, nonlinear curve that looks like that, it will predict the learning behavior, and the prediction was this curve, which you can see is almost, this is the picture that I just showed you, that they put it side by side to see the comparison. So it's quite remarkable, just a simple memristor already can mimic the learning pattern of neurons. Now, so I just shown you that synapses are indeed memristors. Now I want to show you that the axons are made of memristor. This is a typical axon, this sort of cable, and the standard model of that is that you have a whole bunch of resistors interrupted by these red boxes, and these red boxes turn out to be the Husky-Huxley famous circuit model, the Nobel Prize that they won for that. And what they didn't realize, of course, was that these two elements that they called time-varying conductances are in fact memristors. And if you just look at the definition of that Professor Kang did in his thesis as well, this is an ideal memristor. It's not even an approximation. So this, what I'm saying is that the axons are made of memristor as well. But there are two kinds of memristors. The one on the synapses are what I call locally passive, meaning they're non-volatile. You don't need any batteries. Whereas axons, those are generating those signals. Obviously, there is no such thing as a free lunch. You got to have a power supply, and those are active memristors. The reason, by the way, that synapses have got to be non-volatile is because there are so many synapses there. And if you just assume that we consume only 1 nanowatt of power, you would find out that we would require a 10 to the 6 or 1 megawatt to power your brain. And we know that our brain consumes less than 20 watts of power. So synapses got to be non-volatile. Whereas axons are locally active, you need a power supply, and the power supply is known. This is the potassium-sodium pump that uses ATP. So ATP is the energy peers in that sense. So I've just shown you the first part of my talk that the memristors are, in fact, the building blocks of both the synapses and the axons, and therefore our brain. Okay, so for the rest of my talk now, I want to start to show you what I call toy examples of memristor learning. For the first time, one can learn things using a circuit element. And I want to call your attention to this very famous book by Eric Kandel, who actually, when he accepted the Nobel Prize, actually said that the Nobel Prize belongs to this little snail. And the reason is because without that, he would not have been able to obtain all this data and experiment. And so this snail is very interesting. It has a gill, which is for respiration. It's a sea snail, so you need to respiration. And there's a little siphon here. Both of them are very sensitive, so if they sense any danger, immediately they will withdraw and hide, okay? So what Kandel did was to touch it gently with a paintbrush, and immediately it would withdraw as he expected. And then in about 5 minutes, it will come back out again, and then Kandel would touch it again, and he would withdraw again, and he repeated a number of times, and Kandel suddenly realized that there's something interesting here, because the rate of withdrawal is not as urgent anymore. So he actually took measurements these are real measurements on a neuron. So in the first instance, this action potential triggers the withdrawal like that. And then the next time he did it, the action potential is always the same, but the motor neuron, you see, much smaller. And so every time he already showed 5 of them. He had about say 20. So this is the first one, the second, the 5th experiment. So these are all real data. Okay. Now the important thing here is that the response gets smaller and smaller. Okay, because the little snail realized that it's not so dangerous anymore. And I call this. By the way, I gave this talk in France just last summer, so I am using the same slide. And for the French audience, I call this the déjà vu response, because there's the real technical term is called habituation, but the French cannot pronounce H. So if I say habituation, they don't understand, so they love déjà vu. And so déjà vu response is learning to recognize and ignore benign and boring stimulus. Okay, and perhaps the simplest form of learning is habituation. All of us use habituation every day to help us learn not to attend or respond to irrelevant stimuli. Now I want to show you a toy example of a memristor that will do the same thing. So if you take a simple memristor and suppose you this is the horizontal axis is the flux. So if you apply a process just like equivalent to touching with a paintbrush, every time you do that, this voltage is being integrated up because it's the flux that counts. So as it integrates up, you move up this curve, and the slope, remember, is the conductance. So the conductance gets less and less. You get less and less current. So this is the current. So this is the equivalent of the response of the snail. You see, it gets less and less. And so this is a toy example that demonstrates that a single memristor can learn. And you can remember, to be able to do this, you have to remember. And the memristor, one memory can already do that. Okay? So learning, therefore, is impossible without memristors. Without memory, and memristor has that capability. Okay? Now, it turned out that déjà vu response is quite universal. The mechanism is the same in all animals with a nervous system from simple invertebrate to mammals. And in fact, in Professor Kander's book, he actually mentioned this interesting experiment. So to show you that déjà vu applies, in fact, not only to danger alert. Here is a male and female mouse courting each other. And the next thing Kander observed is that when you are attracted to that voluptuous female, such as the one on the right, a male rat will have sex with her 6 or 7 times in a period of 1 or 2 hours. And after the last copulation, he appears exhausted and becomes inactive for 30 minutes or more. So the 2 rats are so bored, in fact, of each other that they even refuse to face each other. You can see they don't face each other anymore. Okay, they were so upset. They are so bored. Well, but what Kander was saying is that this is not fatigue, because he found that the apparently exhausted male rat will instantly resume his passionate sexual repertoire if he encounters moments later a new seductive female. So that's déjà vu, okay? And I have a cartoon for that. There is the middle-aged lady trying to stimulate his boring husband. So he say, response, and he said, what's the matter? And the husband say, it's déjà vu. Okay? So that's sort of an up cartoon, I believe that. And okay, now the next episode I want to tell you is HM. So who is HM? Well, HM is a man that has been in the book of every one interested in molecular biology of the brain for the last 40 years or so. And that's because he has no hippocampus. And the reason is to prevent uncontrollable epileptic seizure. The doctor will perform a surgery on him in 1953, and by removing a small part of the brain that's called the hippocampus. I remember the word hippocampus because we'll come back to that. hippocampus is this little object right here, buried down inside the brain. Now, hippocampus is going to be quite fundamental, it turned out, for memory. And so after it was removed, HM, he was always called HM because to protect his identity, But when asked how old he is, HM invariably respond to say about 30. That was about 2 months' time, remember, 1953, okay? In HM's word, Harry Truman is always president. Black and white television is a novelty, and furniture made out of chrome and veneer still seem to like a good idea. His time is frozen. By the way, HM finally passed away last December, and that we now know who he is. He is Henry Molaison, a very gentle human being that is contributed a great deal to understanding of memory. And so fast forward 20 years later, we come back to this famous paper I told you early on, 1973, 2 years after my Memristor paper. Bliss and Lomo found that tetanus is just a fancy word for saying a pulse strain of voltages or signals. He found that excitation with in the hippocampus, by the way. They knew about the important hippocampus, so they tried there, and they found that this excitation enhances the synaptic response to a single input pulse. In other words, if you imagine that this is the hippocampus, if you first put in a pulse signal, and let's say this is the response, so what they did is now they would put in first a train of pulses, and then you wait for 5 hours. So this is what we would, if we do that, after 5 hours, things disappear. So if you would put in the same signal, you would get the same thing, but no, we found out that suddenly you get a bigger response. So in other words, they discovered for the first time what's called long-time memory. Long-term, they finally remember. Okay, I will show you now a toy Memristor circuit that would actually imitate that behavior. So this, if you just take a Memristor with just 2 segments like that, and so this would be conductance. So this, because it's present in flux, okay? So this would be low conductance, and this would be high conductance. And so if you, in the beginning, you are, say, at 0 initial condition, you put in the pulse, you're in this region, so you have a small response because the conductance is small. Now, if you would, instead of doing that, you put in a pulse strain first, like what Lomo did, and that pulse strain will integrate up, so you are, as it integrates, it moves up, and finally, after a sufficient number, it would enter this high conductance region. And then of course, the Memristor will remember that after you turn it off, it remembers that that's what a Memristor is. And so, if you now wait 5 hours later and put in the same input pulse, you suddenly get something much bigger, which is exactly what was observed biologically. So this is the second toy example that demonstrates what I just said about the role of Memristor playing. The next episode I want to tell you is very interesting because it comes from one of my favorite authors, Remembrance of Things Past, Marcel Proust. He is, by the way, in my opinion, I may not agree, is, in my opinion, the deepest and greatest novel ever written. For those of you who did not know what this is the 3-volume Marcel Proust novel. Okay, and this, believe me, this is fundamental. Okay, he doesn't know a thing about neurobiology, but everything he said, his observation, is all about Memristor and memory. Okay, so Remembrance of Things Past, that's the title of the book, is just a poetic equivalence of associative memory, in my opinion. And I want to give you a quote. If you just look at Volume 1, page 48, you will see to what I'm going to tell you about. This is widely quoted by people now. Marcel Proust, when he was younger, his parents would bring him to visit his aunt Leonie in the city that in the book is called Combray. It's a fictitious city, but the real city that I visited, in fact, just last summer, is called Ilia. And they honored him by calling Ilia Combray. That's the city. If you ever go to Paris, but an hour and a half from there, you will see his museum. And in this, so when they visit his aunt Leonie, and would always serve him, and said here, okay? She would send for one of those squat plum little cakes called Petit Madeleine. And I raised to my lips a spoonful of tea in which I had soaked the morsel. No sooner had the warm liquid mixed with the crumbs touched my palate than a shudder ran through, and I stopped intent upon the extraordinary thing that was happening to me, an exquisite pleasure that invaded my senses. What he is saying is the following. This is the Petit Madeleine, and this is the tea, and it had to be together. If he just took, and it was widely described, he was such perceptive. If he just took the Madeleine, he doesn't remember anything, just the tea, nothing. But the two together, he would, even when he was about 20 years later, he would immediately recall everything of his beautiful village, Cambrai, and the village church, etc. He was talking about associative memory. This is the topic that I want to talk about today. He was the first person to realize that importance. Proust had intuited the anatomy about smell and taste. So his smell, because the tea has this flavor, and the taste of the Madeleine, okay? He had intuited them as the processing center, which I now call this the Proustian hippocampus, okay? Because he did that long before it was confirmed by neuroscientists. He used the taste of Madeleine and smell to channel his childhood. Mathematically, I would say that this put him in the basin of attraction, of the villages, of everything, the recollection. Now, neuroscientists now know Proust was right, because in this famous paper in Science by Hertz, a psychologist from Brown, has shown that our senses of smell and taste are uniquely sentimental. And why? Because smell and taste are the only senses that connect directly to the hippocampus, the center of the brain's long-term memory. In other words, long before HM, Proust already realized that where the location, well, he didn't know the location, but he know that wherever it has to have these two senses, and that's exactly the hippocampus. So, and this whole book is incredibly detailed in going through all of these different episodes that I'm going to be talking a bit more later on. So we're talking about associated memory, and this is before Pavlov's famous experiment. Pavlov is famous for this famous experiment that most of you, I'm sure, have read about. And this has to do with, he would have a dog, and he would ring a bell, of course, and the dog, don't care about bells, so he didn't behave strangely. But if you give him a steak, the dog would salivate. And that's because biologically, the evolution did so because the salivate needs the enzyme to digest the meat, okay? And so why should the dog be interested in the bell? So he doesn't salivate. But then Pavlov has a good sense of first showing the meat, and then follow almost immediately with the bell. And he did that a few times, and then he went an hour or so, and then next time he rang the bell, the dog salivates. That is the famous experiment, that the dog associated memory. This whole phenomenon had been predicted or described in a non-technical way in Proust's books. So now in a very interesting paper by Persian, who is here today, by the way, and Deventra, they managed to show that if you take two memristors and a certain neuron, they would be able to imitate this behavior. And this is taken from their paper. So the first input is the meat, the dog with the steak. The second input is just the bell. So first he would show just the bell, and of course there's no output. And when he shows only the meat, there is an output. You can see it's aligned. When he shows only the bell, there was nothing. And he shows only the meat, there was an output as expected. This is the first part of the experiment. Now he would put Persian would put in both the meat and the bell at the same time. And they overlap. So that's the learning period. So after a while, after it's learned, when person put in just the input, there is an output. This is just like the bell, ringing the bell without the meat, the dog will salivate. So this is a demonstration that even 2 memristors is enough to emulate. I call them toy example, by the way, because they're so simple and already demonstrate point. Now the next experiment I want to show you is by published in the Physical Review in 2008 by a famous group from Japan, and Kuramoto and his group. Now I want to tell you this experiment. This is an experiment about amoeba. We all know, by the way, amoeba is just a one-cell mechanism, and they don't even have a brain, you know. But the amoeba, it's interesting. The amoeba will move. By the way, you may not, because you know it moves, but move very slowly, about 1 centimeter per hour. So this Japanese scientist made an experimental setup, a tube, a conveyor, long enough that, and with all those cameras that you can monitor, and then there is a duct where you can pump in air and humidity so you can control them. So the amoeba turned out would move only when it's about 26 degrees centigrade. That's the ideal temperature. They would love to move. But if you just lower the temperature by so much, or just 3 degrees, it will instantly stop moving. It's just like if I put you suddenly in the North Pole, you do the same thing. You would stop moving too. So this is the experiment, and so imagine now this person was looking at the screen from all this automated instrument, and so this amoeba is moving left to right and right, and now so he just typed in. So this is at 26 degrees, the normal temperature. The amoeba was moving, and then he would put in 3 degrees later, and then amoeba would stop. So from this experiment, I will show you the data. So these are the 3, 1 hour. It is spaced 1 hour apart, okay? And so as soon as it goes from 26 to 23, the amoeba, this is the velocity of amoeba, very slow, but it moves. It's not zeros. It's 0 is when it doesn't move. But here, whenever you inject, it stops moving, and then it will recover, and then after 1 hour, you inject 3 degrees lower, it stops moving. It recovers after 3 hours, it stops moving. Of course, that's what you expect. But what's interesting is the Japanese researchers then stop doing it, but the amoeba, after 1 hour, will stop. So the amoeba suddenly learn that there is something periodic. You know, they learn the periods, 1 hour. So after 1 hour, they thought something is going to come out, they stop. That's incredible. They don't have a brain, remember. And after that, you wait for 5 days. This 1 hour is. After 5 hours, the Japanese scientists put in another pulse. And the amoeba, of course, after a while, the amoeba realized that, like deja vu, they stopped doing that. But they learn it. So that the next time this is injected, the amoeba would, of course, stop. And then without any further learning, they already learned. It would stop another hour, even though there was no input. It was same temperature. In another hour, it would stop again. This is quite remarkable. And the interesting thing about this paper by Persian and Debentra is that they were able to demonstrate that amoeba can do the same thing. And I will show you the circuit. This is the circuit. It is just RLC plus a memristor there. Okay, and this is the membristance curve. So with this, I will just show you their results, since I don't want to take too much time. So when Debentra and Persian injected 3 periodic input, you can see that the response, even afterward, is quite big, just like the amoeba has learned and with the right period. And then after a long time, when they injected again, a single pulse, the circuit learn and will respond at the correct period. But now they will repeat experiments just like the Japanese scientists. They will put something that is not periodic. So let's say this 1 hour, 2 hours, and then 3, 4 hours. It's not periodic. And the amoeba would not do anything. If it's not periodic, the amoeba doesn't learn. Okay? So sure enough, for the same circuit that they have, they injected this, and you can see that the response is almost nothing. And after 5 hours, put in another input, there is no response after that. So this is an excellent sort of imitation. And they actually look at the memristor. In the first case, where the memristor learns with the 3 periodic input, the learning is that in the beginning, the learning period, the memristor is changing. You're going around that curve, and suddenly, when it's finally learned, they change to another curve part. This is the learning period, and then it will stay there. It remembers that. Okay, so that's how this is how that works. Okay, and then for the second case when it's not periodic, they have also shown that the memristor doesn't change much. It doesn't switch up, so that's why it doesn't display the behavior. So it's almost a perfect imitation of the real amoeba thing. Okay, so you have seen a number of all these episodes already, and now I want to go back to Proust. Okay, and now Proust. By the way, that book is 3,200 pages. It's an incredibly long book, and most people consider him to be a literary genius. And one of the sentences are very long. One of the sentences is about 958 words long. I mean, it's incredibly, but the more you read it, the more you appreciate how perceptive he is in being able to understand behavior. You know, he was not a scientist at all, but he is so perceptive. He realized there's something in the brain that is making this happen. So if you have spend the time and actually read through the book, you will see that it's actually sprinkled, not just one part, all over, with many episodes of what I call associated memory, although he didn't know about it. But he was, all these episodes that he is reporting in very poetic way, and even the English translation, which the French are very upset because they say it's not romantic enough, okay? Because Proust is such a wonderful writer. It's so required reading in all French school. It's classic. Like, many people thought he is the equivalent of Shakespeare, Ulysses, all put together. And he lived in the same generation as Hemingway, by the way, and James Joyce. But although they didn't actually knew each other apparently. Okay, so now I just showed you earlier page 48 in volume 1. Now I want to go to jump to volume 3 just to since I'm out of time. But I want to in volume 3, page 64. I know you can read that, so I reproduce it for you. And so before I show you this, I'm going to tell you what happened. This is the last chapter of the 3rd volume, and he was reporting. He went to he was much older then. So he was reporting in a very poetic way that he attended a ball. Actually it's not a masquerade ball, but it's just a ball. And then he suddenly realized that the people there are strange. They look like puppets. The faces are very strange. But then he realized after looking more closely, he said, "Well, look, they resembled those friends of mine or acquaintances of mine when I was 10 years old, 20 years old, And so suddenly he realized that these are the same people, okay? But the way he described it is so poetic. I want to read a paragraph for you, okay? And so he said, a puppet show, that's the ball, okay? Yes, but one in which, in order to identify the puppets with the people whom one had known in the past, it was necessary to read what was written on several planes. Now, when you say several planes, read that as several different input, like the Madeleine and the T, for example. So you need to associate. So this is language, say several planes at once. Place that lay behind visible aspects of the puppets and give them depth. These were puppets bathed in the immaterial colors of the years, puppets which exteriorized time. And throughout this book, he was talking about time. It's incredible because time is memory. In fact, the French title of the correct translation, if you were translating at that time, the correct French title is actually In Search of Lost Time. But the English translator was much more endeavored with the Victorian prose, so he borrowed a sentence from Shakespeare's sonnet that's called Remembrance of Things Past. Okay, but he was talking really about time, and of course, time is memory. That's exactly what he's talking about. So if you don't know about what I'm talking about, you would appreciate it. But now that I'm telling you this, you would really enjoy it. Every time you see he's talking about time and describe the episode, you should ring a bell and you begin to associate, just like what I say now, with associated memory. So this is the beautiful book that is full of how our brain works. And now exactly how the associated memory works, I will give you a sort of a qualitative explanation. When you associate memory, you think of this in a very high dimensional space where every point, every valley is a picture, let's say, okay, or a story like the village church that when the Madeline and the tea would trigger, he would finally recall the beautiful village church and his Aunt Leonie, etc. By the way, this beautiful little town is still intact. You see the village church. Everything he described is in that little town. It's almost like the whole town is like a museum, and the house is a museum now also. Okay, and so imagine now the association here. The model is you put it in. Let's say the village church is somewhere here. So if you just have the Madeline, it would go down somewhere else. But if you have both the tea and the Madeline, you're somehow in the right basin of attraction. You will sink down to the right place, and that's really the dynamic mechanism of recalling. You know, if you want to be scientific about it. And so what he's talking about is these puppets, these faces. It turned out that those were grown. They have grown old, but when they grown old, there are some basic features that stays. And he was able to. So what he's talking about is that somehow, let's say that was one of the puppet's face, and even though it's different, it has grown old, it has wrinkles, it looks almost like a cadaver, and yet it has preserved enough features that he would sink down to the right place, and he would say, "This is John, my old friend," for example. Okay, so this associated memory is actually how we work, and I want to show you a picture that. I think most of you, at least in my age, will probably remember. If you have seen this movie, you see this picture, you associate immediately, of course, with Marilyn Monroe. Okay, you don't need to see her face; you know it's Marilyn Monroe. It's exactly the same thing. You are associating with the thing. Well, I will show you. We have just recently wrote a paper where we use a CNN, but by the way, there's a conference and continuing after this. On another subject, CNN, and there, if you apply one of those algorithms and put a Memristor as part of the element there, you will be able to do associated memory. Now, remember, when you associate, it doesn't have to be a part of the original thing because it's all wrinkled. You just have to be close enough to be there. So I want to show you this picture. I think most of you probably recognize. Who is he? Of course, it's Obama. Okay. And so a good picture of Obama is on the right. Now, of course, I'm going to turn this around, and you can see that it's quite different. But you associate, even back inverted, okay? Somehow, I have just twisted this. This was done by Ito, from my colleague, and he just reversed part of the mouth. And but he has enough feature that you know you can retrieve that. Okay, so in this paper that we are publishing, this is the distorted Obama, okay? And so we deliberately do this to show you that there's enough associated power to be able to retrieve things, even it was upside down and and distorted. This is the binary version of that because everything is done in binary. So this is this is the input to the circuit, initial binary image, and from here, it is retrieved. So there are many pictures stored in there. There is of other people, including the correct Obama picture, but just by showing this one, which is a distorted, like the wrinkle face of a Proust episodes, is enough to trigger, to associate, that will bring out the correct one. This one, if I now put back in color, is the correct picture. Okay, so and that was using a CNN with a Memristor, by the way. Okay, so but Memristor is necessary because you have anytime you want to learn, you have to have a place to store the intermediate results, and you keep inching up and down that learning curve of Memristor until you get it done. Okay, so let me point out that this is what creativity. In fact, if you don't want to learn exactly, if it's the exact reproduction, and that's no good. It's just like in DNA. If we do not have mutations, we will never evolve, right? You have to have something different. And so it turned out that I claim that associative memory is essential for creativity. One creates by synthesizing fragments of past experiences. Okay. And so you have learned, you have experienced it, but you take part of that and you create. So it does not have to be the original one. In fact, if it is the original one that is stored like the Obama, it's not creative. What's interesting about our brain is that we can create from something that is not there. And no one said this better than Mark Twain. Mark Twain said, when I was young, I could remember anything, whether it happened or not. Okay? And that's associative memory. So finally, I want to come to my conclusion. What you have seen, by the way, is that the amoeba does not, as you remember, the amoeba doesn't have a brain, okay? But it has a mind, okay? And so you do not need the neurons, in fact, to have intelligence. And so I have a prediction. I call it my vision 100 years from now. I would claim, my crystal ball, say Memristor brains will be controlled by Memristor minds. Memristor minds has no neurons, okay? And so the brain, remember, is just the hardware, okay? And I have a cartoon that sort of dramatizes this. Here's a cartoon years from now. The computer is going to say, I need to upgrade my brain to be compatible with this new software. We have become slaves to the machine, okay? And so finally, I would end up my talk with, we're talking about creativity. We're talking about to be creative, to be logical. I end up usually with what I call my favorite bear story. This is a dangerous grizzly bear. And this is a story that some of you may have heard from my earlier talk. It has to do with, there's an old story. I call it old story because this is a favorite story for many people. And the story is about a philosopher who runs when a bear charges him and his friend. And his friend happened to be a mathematician who's very precise. Everything has to be logical, has to be exact, And so when the bear started to charge, the philosopher started to run. But the mathematician say, it's no good. You will never outrun a bear. He was telling the philosopher, why do you run? He was being very, very logical, very exact. But the philosopher say, I don't have to. I only have to outrun you. Well, that's intelligence. That's being creative, okay? And if you have Memristors, someday you are going to be as creative as a philosopher. End of my talk.
Thank you, Leon.
I guess time is up.
I'd like to present to you a little souvenir.
Thank you very much.
Yeah.